Okay, everyone, good afternoon. Welcome to our fourth lecture for the MSD 780 Postgraduate Dynamics course. Okay, so without spending too much time on perhaps an overview, I think by now we are well acquainted with the mind map that we've been working with up to now, using the pendulum rod to explain the underlying principles behind Nicoravecius body coordinate planar multi-body dynamics algorithm. I'm perhaps just going to give you a quick review of what we did last week with regards to the pendulum rod and how we evaluated it. So we essentially started off with an undriven pendulum rod, a pendulum rod that is simply subjected to gravity, and we want to go and check what the reaction forces are and what the actual motion of the pendulum rod under this gravitational force is. And that is essentially what the prime concern was around the undriven pendulum rod. In section 5, we jumped into the kinematic and the inverse dynamic analysis of the driven pendulum rod. And we also had a bit of a look at the forward dynamic analysis of this rod as well. We started with the inverse dynamic analysis, where we said we have some sort of an angular acceleration that has to be specified on the pendulum rod. And we want to go and check what is the effect of this going to be on the motion of the system as well as on the reaction forces. And we noted as well, since we now have a driven pendulum rod, we now have a driver constraint that is associated with that angular acceleration that we specify on the pendulum rod. We were able to essentially integrate twice with respect to time to end up with our angle of the pendulum rod as a function of time, and this formed our driver constraint function that we gave to DAP-BC as input. With regards to the forward dynamic analysis, that was simply a case of applying a constant torque to the model. And what we saw over there was if we apply the constant torque over the entire time interval, what we end up with is a situation where the angular acceleration is going to start to oscillate. And what we can also do is combine the two analyses with one another. We can look at a driven and an undriven pendulum, or sorry, not a driven and a driven, undriven, a forward and an inverse dynamic analysis on the pendulum rod. That was the case where we then specified both the angular acceleration on the pendulum rod and we also specified the torque on the rod. And what DAP-BC was able to very effectively do is to apply a braking torque so that when we expect to see that deviation in the angular acceleration, DAP-BC essentially corrects the motion of the system or the dynamics and the reaction forces and torques of the pendulum rod to ensure that we always remain at that constant angular acceleration that we specified on the system. So we're going to have a look at those three examples, or actually the two examples, the inverse, the forward, and then also the combined dynamic analysis again today. But before we do that, I perhaps want to give you a bit more information with regards to the forward dynamic analysis of the pendulum rod. And there are two formulations that we are going to look at over here. Firstly, an unconstrained formulation, and then section 13.2 of the PMD textbook will deal with the constrained formulation. Now, jumping into section 13.1, the unconstrained equations of motion can be expressed in the following form in equation 13.1. So this is an equation that you will be well acquainted with at this stage. We essentially have our mass matrix multiplied by some sort of a coordinate vector or an acceleration vector over here, which is then equal to all of our net forces that act on the system, denoted by this H in bold. Now, this equation may represent the equations of motion for either a system of unconstrained particles, a system of unconstrained bodies, or an open chain system formulated by the joint coordinate formulation. These equations are treated as linear algebraic equations when the unknowns are the accelerations, and when the unknowns are the coordinates and the velocities, the same equations are treated as second-order ordinary differential equations. And on that note, we can then look at how we treat the equations of motion as second-order equations and how we integrate these equations numerically. And in that case, we specify two vectors. Firstly, we have a u vector, which is simply the coordinates and the velocities combined. And then if we take the time-based derivative of the u vector, we end up with u dot, which is simply q dot, so the velocities, and then q double dot, the accelerations. Now, if we integrate the array u dot containing the velocities and the accelerations, we obtain the array u containing the coordinates and the velocities at the next time step. So already you can see, if you are well acquainted with the numerical methods, you can already see that there's some sort of an integration that is going to happen, and we are going to step through a certain time interval that we have at our disposal. So this already tells me that there's going to be some sort of an iterative solver that I will need to apply to this type of problem. Now, obviously, this requires a set of initial values for the coordinates and velocities to start the integration process. And looking at example 13.1, if we have a system of two unconstrained bodies, so in this case, body 1 and body 2 are not constrained through kinematic or revolute joints. In this case, we simply have a spring and a damper connecting the systems. A spring connects the bodies at A and C, and a damper connects the point B of body 1 to the ground at Q. The gravity acts on the system in the negative y direction, and the lengths of links 1 and 2 are also given, with the other constants given in this block here at the bottom. And for the instance shown, the bodies have the following coordinates and velocity. So they give us the coordinates, they also give the angle of each body, and then also the velocities and the angular speeds that we have for each body. And we can refer to this system of two unconstrained bodies and define the necessary integration arrays to solve the equations of motion for this system using the body coordinate formulation. Now the solution over here is simply to combine your q dot q and q double dot vectors in the correct form so that you end up with the u and u dot vectors. And this is shown over here. So you just have r1, phi1, r2, and phi2. If we write all of them in the correct form, we end up with our u vector, which is first the coordinates associated with body 1, then the coordinates associated with body 2. Then we just place this separator line in over here, and let me perhaps zoom in a bit as well. We just have a separator line that we place over here, and below that we now consider the velocities of body 1 and the velocities of body 2. So of course, if I go one step further and I derive u, I get this u dot, and that will then just be r dot 1, phi dot 1, r dot 2, phi dot 2 above the separator line, and below the line I then have the accelerations. So accelerations for body 1 and then the accelerations for body 2. And this is the form that we will use when we run a body coordinate formulation problem. We don't really have to worry about setting up these vectors. We just need to be aware that there's going to be some sort of an initial condition that we need to specify once we start off with the dynamic analysis. So we need to give it an initial guess or an initial condition so that the integration can start. With that in mind, we can then move over to the initial value problems. Now, most general numerical algorithms are developed to solve first-order differential equations. And the first-order differential equation is simply written as u dot, which is a function of u and t. Now, if we consider all of these parameters over here, t is referred to as an independent variable, and u, which is a function of t, is then considered the dependent variable because its value depends on the value of t. Equation 13.3 also has a family of solutions u of t. The choice of an initial value u0 serves to determine one of the solutions of the family. So the initial value u0 could be defined for any value of t0, although we often assume that for transformation we have that t0, so our initial time step is in any case 0 seconds. And this does not affect the solution or the methods used to approximate the solution. In general, if independent variables are involved and n first-order differential equations are available, then equation 13.3 is simply written in its vector form. So in this case, we have a bolded u dot, which is equal to f, which is so the function, and u is then also a vector, t is still a scalar independent variable that we consider. And now we have a set of initial conditions U naught. In dynamics problems, T represents time and it may not appear explicitly in the equations. In dynamics problems, T represents, well, this is just an iteration of what we said in this point over here, but it's just important to note this, that you essentially have either explicit or implicit equations in which the time function appears, and our solution or our solver that we're going to use will depend on whether it's an explicit or implicit equation of time. So solving the initial value problems involves a step-by-step process in which a sequence of discrete points t0, t1 up to tn, where n is the number of time steps that you have, is generated. And the discrete points may have either constant or variable spacing. So delta ti is simply equal to the I plus 1 time step minus the previous time step, where delta ti is then the step size for any discrete point ti. And at each point ti, the solution of the vector u as a function of ti is approximated by a number ui. Now, since no numerical algorithm is capable of finding u as a function of ti exactly, we instead impose an error to determine whether the solution is accurate enough. And in this case, we simply call it epsilon I, which is then the absolute value or the error between u as a function of ti and ui. And this is defined to represent the total error at time t equal to ti. The total error consists of two components that we need to take into account. Firstly, we have a truncation error, and this depends on the nature of the numerical algorithm used in computing ui. And in the PMD textbook, when the term numerical error is used, it is referring to the truncation error. But we also have a round-off error, and the round-off error has to do with the machine precision. So due to the finite word length in a computer will never be 100% accurate. You do have some accuracy that you lose once you do these calculations. We just need to be aware of that once we calculate the error, and we need to take that into account as well. An algorithm can then be categorized as either explicit or implicit. In an explicit algorithm, we evaluate u I plus 1 strictly as a function of u, which is a function of ti plus 1. And ui is then also simply a function of u as a function of ti. So we can explicitly write the ith u value in terms of time and in terms of the u as a function of t dependent variable that we have. However, an implicit algorithm is iterative. In these algorithms, an estimate of ui plus 1 is required to actually start the iteration of the formula. And in order to obtain a relatively good estimate for ui plus 1, an explicit formula can be basically joined onto this implicit formula, so as a sub-algorithm. And this step is then known as a predictor step. Then the implicit formula is used to correct the predicted value of ui plus 1, and this is simply called the corrector step. And normally an algorithm iterates on this corrector step. Now, with regards to what type of solvers that we can use, although there exist many algorithms for solving these initial value problems, most of them are based on either a Taylor series expansion or a polynomial approximation. For the Taylor series expansion, algorithms that are based on Taylor series require the derivatives of the function with respect to t, and a kth order algorithm needs the derivatives up to k minus 1. And these derivatives in general are not readily available, and therefore the higher order algorithms with better accuracy are not computationally efficient. Now, polynomial approximation is simply setting up an actual polynomial to capture the data that you have available. And I believe we're going to delve into that a bit later on, but just take note that a polynomial approximation can be used when we solve these initial value problems as well. A classical theory asserts that any continuous function can be approximated arbitrarily within any closed interval by this polynomial approximation of sufficiently high degree, even if the solution is not a polynomial. In view of this theory, a polynomial of sufficiently high order can, in principle, be used to calculate u as a function of ti plus 1 to any desired accuracy. And a kth degree polynomial is then referred to as an algorithm of order k, and in practice, the amount of computation increases with the order of the polynomial. In most polynomial approximation algorithms, information from previous time steps is utilized to compute ui plus 1, and an algorithm that utilizes information from time steps prior to ti is then called a multi-step algorithm. The accuracy of an algorithm is directly proportional to its order, so in general, the higher the order, the more accurate the algorithm can predict the solution, of course at the cost of the actual computation time. Now, another commonly used family of explicit algorithms is the Runge-Kutta method that can be considered as a revised form of the Taylor algorithms. And in PMD section 13.1.2, Nekravesh reviews the fourth order Runge-Kutta algorithm. Now, we are perhaps more interested in the actual integration time step size. And before I jump into this, I first need to iterate that when we talk about the integration time step size, it's not the same as when we look at the reporting time step. You'll remember that when we run through DAP-BC, one of the inputs that we need to give is the reporting time step. The reporting time step simply has to do with at what intervals does DAP-BC have to print out the data or post-process the data. The integration time step, however, is sensitive to the actual algorithm that is being used. So this differs from the reporting time step, and it's in any case calculated inside of MATLAB or inside of the DAP-BC workbench. So we don't have direct control over the integration time step size. We can only say how fine we want our reporting time step to be. Now, an important issue in using constant time step numerical integration algorithms, such as the fourth order Runge-Kutta, is the selection of a proper time step. A large step may cause erroneous results. A time step too small may yield accurate results while increasing the computation time too much. Therefore, it is important to choose a reasonably small time step size to obtain accurate results without unnecessarily increasing the computation time. So the size of the integration time steps should be adjusted based on the natural frequencies of a system. The higher the frequency, the smaller the time step has to be. And to better illustrate this, we can look at figure 13.1a. So this is simply a one-dimensional case where we have a mass that is connected to a spring. If we go and write the equation of motion for the system, then it ends up giving us mx double dot plus kx equal to 0. We divide throughout by the mass of the object that is connected to the spring, and we end up with x double dot plus k over m times x equal to 0. And we also know that this system exhibits an oscillatory motion, and therefore the solution to this differential equation can be assumed to be of the form x equal to some amplitude multiplied by cosine omega t plus phi, which is then the phase shift. Now, in this equation, omega is the natural frequency, and we simply equate this to the square root of the stiffness of the spring divided by the mass of the object connected to the spring. The period of the oscillation associated with omega is then simply calculated as tau, which is equal to 2 pi over omega. And if equation 13.8 is solved numerically, the step size delta t must be much smaller than the period tau. A reasonable value for delta t could then be that delta t must be smaller than 1/10 of the period that we calculated. So if we substitute some values in, we can say that the mass is 1 kilograms, the stiffness of the spring is 100 Newton per meter, and so we calculate the time period from equation 1311 as 0.628. So in accordance with equation 13.12, we then get that our time step should be smaller than 0.06 seconds. As another example, we can consider the single pendulum shown in figure 13.1b. So essentially the pendulum rod that we've been working with up to now. And for a rod with a length L and a mass m, the moment of inertia is 1/12 ml squared. This is one of the equations or the formulas that we get from a formula sheet that gives us the moment of inertia about the center of mass of a slender rod. If the only external force is the gravity, the equation of motion in the joint coordinate formulation is then written in this form that we have over here. And for oscillations of small amplitude, sine theta can be replaced by theta. And therefore, this equation is then simply linearized to the second part that we see over here in equation 13.13. So continuing with the previous analogy, we simply use whatever is in front of the positional variable, and we simply take the square root of that to get our natural frequency. In this case, omega will then be the square root of 3g over 2l. If we once again assume some values for the pendulum rod, L is equal to 1, G equal to 9.81, the time period is found to be 3.836 seconds. So therefore, our integration time step should be smaller than 1/10 of this value, so that is smaller than 0.38 seconds. And for our pendulum rod, which we are actually working with up to now, has a length of 0.6 meters, then our natural frequency is given as 4.9523 hertz. And if we then use equation 1311, which is the calculation of the period of the oscillation, then we end up with a period of 1.2687 seconds. So our integration time step would need to be smaller than 0.127 seconds. Now, to see how damping affects the natural frequencies and hence the selection of the time steps, we can revise equation 13.8 to include damping, where dc is then simply the damping coefficient. So now our equation of motion becomes mx double dot plus dc times x dot plus x or plus kx is equal to 0. And if we rewrite this by simply dividing by the mass in this case, x double dot, we divide by mass, so it becomes x double dot plus dc over m times x dot plus k over m times x, which is equal to 0. And then we can simply go and write the damping ratio as this zeta parameter over here, which is then equal to the damping coefficient divided by 2 times the square root of the stiffness of the spring multiplied by the mass of the object. And with this definition, we can now rewrite equation 1315 in this form over here in equation 1317. And in this case, omega is still equal to the square root of k over m. This is known as the undamped natural frequency. And then the damped frequency is expressed as omega with the subscript d, which is equal to the undamped natural frequency multiplied by the square root of 1 minus zeta squared. So if we look at figure 13.2, we can now see what the effect of this damping ratio is over here. And for zeta equal to 0, we have an oscillatory response with no damping, with the time period tau equal to 1 second. If, however, the damping ratio is now 0.2, the response begins to decay as long as zeta is between 0 and 1. Then we call the system underdamped. And we note that for this response, omega d is slightly smaller than 2 pi. When zeta is equal to 1, the system is called critically damped. And in that case, the damping frequency over here is equal to 0. But in general, what we see from this is that the damping frequency or the damped frequency is smaller than the undamped natural frequency for the purpose of the time step selection. So we should use the undamped natural frequency as our reference when we do these type of calculations. The mass spring and pendulum rod examples show how the time period of the oscillation can be calculated. However, for more complex systems, the calculation of natural frequencies will not be that simple. And for multi-body systems, the linearization of the equations of motion in explicit form can be rather cumbersome. For systems with more than one degree of freedom, there will be more than one natural frequency as well. And in this case, the highest frequency must be found, and a step size much smaller than the period of the highest frequency must be selected. Since the equations of motion are generally nonlinear in terms of the coordinates, linearization of these equations yields a time step, which is valid only for the configuration around which the system has been linearized. So in a different configuration, the linearization process may yield a different time period and consequently a different time step size. So once again, it doesn't necessarily mean that for a specific configuration, the time step size that we get over there is going to be universal. We need to evaluate it at each configuration. Now, to avoid the difficulties associated with the selection of a proper size for the time step, it is strongly recommended that a variable time step algorithm be used. And many well-developed algorithms are available that determine a proper time step, which will automatically adjust the time step size during the course of the simulation. In MATLAB, we refer to ODE45 as the function that we want to use. So the function ODE45 can be written in this form over here. So we have two outputs and we essentially give it three inputs as well. Those input arguments are then the at example. So this is the function where the equations of motion are constructed and solved. We also have the reporting time interval delta t that should be specified in t span as the starting time, the time interval, and the final time. And then Z is the integration array containing the initial conditions on the variables, so the coordinates and the velocities. If delta t is not stated in t-span, ODE45 will report the results at every integration time step. Now the output of ODE45 contains two arrays, the t and the zt arrays. The column array t contains the time marks of the integration, and the array zt contains the time record of u prime, so the coordinates and the velocities. The accelerations are not returned from ODE45. If the accelerations are needed, they must be recomputed by solving the equations of motion as algebraic equations at every time step. All right, so what this essentially tells us is that we don't need to worry too much about varying the time step from our side. The ODE45 solver in MATLAB is actually able to adjust the integration time step. So we just need to be aware that we are using a variable time step when we calculate parameters in DAP-BC. Okay, so that is then everything for the unconstrained formulation. Before I continue on to the constrained formulation, are there any questions at this stage? All right, I think we're still good. So in that case, I'm then going to continue on to the constrained formulation. The constrained equations of motion should also look quite familiar to you, and you'll remember that we looked at the derivation of these equations in light of the pendulum rod that we looked at. We firstly have our constraint evaluation over here in equation 1319. So that is simply denoted as phi as a function of q equal to 0. If we derive this once, we end up with the second equation 1320. Where the Jacobian matrix now comes into play. And then if we derive this equation, this constraint equation, or this constraint matrix once again, we end up with the accelerations, and this is then also a function of the Jacobian matrix, the accelerations, and then we have this constant lambda over here as well. And then our final equation over here, 1322, is simply to relate the kinematics of the system to the dynamics or the forces. This is just an extended version of the mq double dot equal to h. In this case, we say we still have the mass matrix multiplied by q double dot, but now we have an applied forces matrix or vector plus, and then we can consider our reaction forces as a separate matrix over here, which is simply the Jacobian matrix's transpose multiplied by the lambda or the Lagrange multipliers associated with the reaction forces. Now these equations could represent a system of constrained particles, a set of bodies formulated in body coordinates, or a closed chain system represented by joint coordinates. And in the case of a set of bodies formulated in body coordinates, we refer to the pendulum rod again. and we can go and look at our constraint equation that we got over there for the revolute joint. So this was derived in one of the previous lectures. We derive that once. We get phi q, phi dot, which is then equal to dq dot. That relates to the velocities. Accelerations is just the time derivative of that again. And then our final equation, 1322, is then written in this form as well, where we break up the applied and the reaction forces. Now, these equations can be treated as linear algebraic equations if the coordinates and the velocities are known and the accelerations and Lagrange multipliers are unknown. When the unknowns are the coordinates and the velocities, the same equations must be treated as second-order mixed differential algebraic equations. All right, so in the case of equation 1322, we can append this to equation 1321 to form the following set of equations, or the combined kinematic dynamic analysis, which is then where we consider the mass matrix, the Jacobian matrices, all together as submatrices in a main matrix. And this is then multiplied by our acceleration vector and our Lagrange multipliers, which should then be equal to the applied forces and this constant lambda over here as well. And in our forward dynamics pendulum rod equation 1323 then becomes this form that we have over here. So knowing the coordinates and the velocities, the equations represented by equation 1323 can be solved for q double dot and lambda. Considering equation 1322 as differential equations, two integration arrays are defined similar to the unconstrained formulation. We once again have u and u dot in this case. And for our forward dynamics pendulum rod, this is the form in which we write it. In this case, we have a single body, so we write first the coordinates for body 1 or for the rod, then we write the velocities for body 1, and then u dot is simply the velocities first and then the acceleration, since it's the time derivative of u. If we integrate u dot, which contains the velocities and accelerations, we once again obtain u that contains the coordinates and the velocities for the next time step. So once again, an iteration that we need to perform over here. And this requires a set of initial values for the coordinates and the velocities to start the integration. The initial values for the coordinates and velocities must satisfy the position and velocity constraints respectively. Now the coefficient matrix in equation 1323, so this combined equation that we have over here, contains numerous zero entries. M is a diagonal matrix in body coordinate formulation. So you'll remember for a single body, we have a 3x3 matrix where the diagonals are simply the first two entries are the mass of the body, and then the last entry, diagonal entry, will just be the mass moment of inertia of that body. Everything else is then going to be zero in that submatrix. Then the Jacobian contains many zeros as well, and we also have a zero NC by NC matrix. So depending on the number of constraints that we have, this will be a square matrix of the number of constraints at the lower right corner. Any operation on such a matrix in the process of determining the accelerations and Lagrange multipliers may computationally be inefficient. So to improve the computational efficiency, we can obtain the solution in a two-step process. In that case, we then first rewrite equation 1322 in this form over here. So q double dot is equal to the inverse of the mass matrix multiplied then by the applied forces plus the reaction forces. And for our forward dynamics pendulum rod, equation 1325 is then written in this extended version that we have over here. So all that we do in this case is we just take the inverse of the mass matrix. Since we are working with a diagonal matrix, the inverse is simply 1 over m1, 1 over m1, and 1 over j1, with all other entries still being equal to 0. Then we can substitute the preceding equation, 1325, into 1321 and rearrange the terms to get 1326 in this case. So now we have some multiplication that we perform with the Jacobian and the mass matrix inverse in this case. But if we write it for our forward dynamics pendulum rod, we end up with this extended equation over here. We can do some simplification just considering the actual sizes of the matrices, but what we will end up with is a 2 by 2 square matrix multiplied by our Lagrange multiplier vector, which is then equal to a 2 by 3 matrix multiplied by our applied forces vector in this case. Now, since the product of the Jacobian multiplied by the inverse of the mass matrix multiplied by the transpose of the Jacobian matrix is a square matrix, we first solve equation 1326 for lambda and then solve equation 1325 for q double dot. And we note that in the body coordinate formulation, the mass matrix is a constant diagonal matrix, and therefore the inverse is computed easily and only once, simply as taking the reciprocal of the masses and the moments of inertia. Okay, so that is then the first part that we just wanted to look at, so the constrained equations of motion that we now consider. And next we can now delve into the initial conditions and how they are treated in this case. So solving second order differential equations requires initial conditions on the coordinates and velocities, the same as with the unconstrained formulation. Although these initial conditions must represent the state of the system at the initial time, in general, for unconstrained equations, the initial conditions may be assigned arbitrary values. But when the system is now constrained, so when we have actual joints that connect the bodies to one another, the initial conditions must satisfy the constraints at the position and the velocity levels. And equation 13, 27, and 28 show this. This is simply a breakdown of the position and velocity constraints. So we once again break up the constraint equations for joints, and then we also have driver constraints. So a motor or an actuator that we apply to the system is treated separately from the other joint constraint equations. And then we just find the derivatives, and this is then given in equation 1328. In these equations, we have considered the possibility of driver type constraints that might be present. If we start numerical integration with a set of initial conditions that do not satisfy the constraints, most likely the integrated response will be erroneous. And chapter 14 discusses several methods to assure the initial conditions do not violate the constraints. Now, from our perspective, when we run the DAP-BC program, you'll remember that one of the inputs that we give is whether we want to perform initial condition correction. And it's always good practice to make sure that you click yes in that case, mainly because it ensures that any truncation errors, any round-off errors that you may have made when you provided input in your script are taken into account, reworked, and ensures that all of the connections between the bodies are satisfied. So it just increases the accuracy of the conditions that you specified on the system. This, of course, doesn't mean that you can be negligent when it comes to the specification of your initial conditions. It should still be close to the corrected initial conditions. An example of that would be one of our first lectures where we looked at the graphical representation of a slider crank mechanism. We saw that we could essentially solve the slider crank mechanism in one of two configurations, either with the crank arm being to the right or to the left. Now, if I were to specify my initial conditions more towards the right, then it is very likely that DAP-BC will correct the initial conditions so that I solve the right side slider crank mechanism. If I specified it to the left, DAP-BC would correct my initial conditions to solve the left side slider crank. So we still need to exert some level of accuracy when we specify these initial conditions, but it doesn't have to be to the 16th decimal as an example. We can still make some round-off errors and just make sure that we tick the initial condition correction once we run the DAP-BC workbench. Now, with that being said, we can then look at the general integration procedure as well. So we assume that a multi-body system with a specified number of degrees of freedom is represented by a set of NV coordinates. And in C, the number of constraints is then equal to NV minus NDOF independent kinematic constraints. A process for forward dynamic analysis can then be stated as in the following algorithm. And this is then given as algorithm C as well in the PMD textbook. So what we first need is initial conditions for the coordinates and the velocities. The initial conditions must satisfy the constraints at the coordinate and velocity levels. We then initialize our integration array as U, which is then Q naught and Q dot naught. We establish the time parameters for integration, and we utilize a numerical integrator such as ODE45. We send U and other necessary data to the integrator, and the numerical integrator ODE45 then calculates the outputs and returns the computed coordinates and velocities for every time step. And example 3.5 also illustrates this algorithm that is used. Okay, so that was then the constraint formulation, and that also then wraps up section 6, where we looked at the forward dynamic analysis just from a mathematical perspective. Now, before we jump into the Octave examples, just any questions so far from anyone? Okay, I think we're still good. In that case, I'm then going to jump into Octave, and what we're going to do for the next session of this lecture, or the next part of this lecture, is just to revise what we did for the previous pendulum rod cases that we looked at. I ran through them quite quickly in the previous lecture. In this case, we can just go through them again and make sure that we understand when we're working with a forward dynamic analysis, with the inverse dynamic analysis, and what happens when we combine the analyses. Now, if you go to your DAP BC main folder again, we are going to start off with PR_D in this case. And I just want to open all of its input files again. Okay, so in the case of PR_D, if we go to in forces, you'll remember that we specified over here constant torque on the system. So this was a forward dynamic analysis that we performed. If you look at in joints, the only joint that we specified in this case was the revolute joint, and this is where the pendulum rod is swinging or is hinging on the ground. So we don't have any relative rotation driver that we specify on this system. So technically we're working with a strictly forward dynamic analysis in this case. Now, with regards to I think it's in forces, we also specify the torque to be large enough so that the pendulum rod can swing and overcome the gravitational effect. And we wanted to see what the effect of this was on the kinematics and also then on the reaction forces of the system. And when I ran this problem, let me just move this over. We simply typed in DAP, which folder contains the model, so it's PR_D. Do we want to correct the initial conditions? So as I mentioned, yes, it's always good practice to do this. And then our final time, I think we can do something like 2 seconds in this case, and let's perhaps do a 0.01 reporting time step with 453 function evaluations. So if we once again look at the animation in this case, you'll notice that it starts off fairly slowly, and then as it's going to continue to rotate, it's going to pick up momentum and it's going to continue to accelerate about the revolute joint. Okay, so if we want to look at the post-processing results, we just type in post, and one of the scripts that I made available as well is this postplots.m that we have over here. In this case, we're just not going to consider Lagrange multiplier 3 because we don't have a Lagrange multiplier 3. Remember that the only two Lagrange multipliers that we have in this case is the X and Y reaction forces associated with the revolute joint. We don't have a third Lagrange multiplier because that would apply to a driver constraint that we specify, the relative rotation driver. So I'm just going to switch this off in the script. And just a note as well, if you want to comment out a bunch of lines, you can just type in, let me just show you. So you're just going to type in Control and R, and then it will switch it off. If you want to uncomment lines, it's Control Shift and R. Right, so, but in our case, we want to comment out the Lagrange multiplier 3, and if we're happy with that, I'm just going to go back to the command window, type in post underscore plot, and then it generates all of the plots that I want to look at. And I'm going to start off with figure 1, which is then the circular profile that the pendulum rod is following. So this tells me that, and perhaps I can also zoom in on some of these inaccuracies that we have over here. You'll see that the lines on the circular profile do not intersect with one another or do not coincide with one another. And that is simply because as the system is starting to pick up momentum, the reporting time steps are perhaps not fine enough to capture the inaccuracies between two consecutive points. But overall, we can see that it is following the circular profile. So this already gives us confidence in the results that we are going to get out. Figure 2 is then simply the coordinates, and let me just see if I can open it like this. Okay, maybe I should just hover over it for now. But what you'll see in the case of figure 2 is just the x and y coordinates of the center of mass as a function of time. As we saw from the animation as well, since the pendulum rod is accelerating as time continues, we do expect the oscillations in the x and y coordinates to increase, so the frequency to increase in this case, and that is what is happening with the coordinates. If we then look at, yeah, let me just see, I don't know why it doesn't want to close now, but let's just hover over figure 3 then. So figure 3 is then the velocities, if I'm not mistaken, and I think in this case we see once again the oscillatory effects of that acceleration of the system. Then figure 4, if I just go back over here, so figure 4 is then the actual accelerations that we see for the system. Now in this case we can see that we are applying constant torque. It doesn't necessarily mean that we're going to get a constant angular acceleration out. As a matter of fact, as we continue to apply this torque, it's actually causing the oscillations in the angular accelerations to grow. So we have higher amplitude oscillations after 2 seconds than what we had at the start. And the frequency of the oscillations also increases. So this shows that the angular acceleration of the pendulum rod is not constant, although we specify a constant torque. Figure 5 is then simply the angular position of the pendulum rod. And what is important over here is that DAP BC will continue to add to the angle as it rotates. It's not going to cycle between 0 and 360 degrees. If it starts at 0 degrees and it makes 2 revolutions, it's going to end up at 720 degrees. In this case, these values are simply given in radians, but we can see that the angle is increasing as well. And lastly, we just have the rotational acceleration of the pendulum rod for the applied torque only. And once again, as with the linear accelerations, for the angular accelerations, we can also see that there is some oscillatory effect over here caused by the constant torque that is being applied. And the frequency of these oscillations also increase with time. Now, the second example that we did, and I'm just going to say over here, clear all, close all CLC. Just want to check. So, yeah, I think for PR_E, we then started to look at the relative rotation driver. So in this case, we are now focusing on an inverse dynamic analysis. Just want to open all of its input files as well. But my focus at this stage would then be just to first switch off the torques. So to do this, I can actually just go and remove S2 over here. So now we're not applying any constant torque to the system. We only want to see what the effect is going to be of the driver constraint. So if we specify now a constant angular acceleration on the pendulum rod, what will happen to the system? If I go to in joint, you'll remember that we used a relative rotation driver in this case. So for that, we need to specify the two bodies between which the relative rotation driver is acting, and then also the function index that refers us to the infunct script that we have over here. And this is once again, if we simply go and we specify a constant angular acceleration, I believe it was pi over 60 on the system. If you integrate it twice, you'll get your position, your angular position as a function of time, and that will then be your driver constraint function that you specify over here. So it's a parabolic function, so therefore we simply specify the type of function as a type A function, and we give it the 3 coefficients as input in this case. So now if I go and run DAP again, it asks me which folder contains the model. So this will now be PR_E. I want to correct the initial conditions again, and I end up with the X, Y, and Phi initial conditions, which I specified in the in-body script as well as the X dot, Y dot, and Phi dot, which simply states that the system is starting from rest. So this correlates well with the inputs that I gave to the system. If I now want to go and check what the effect is on the system for the inverse dynamic analysis, I can use a bit of a larger time in this case. So I'm going to make it 30 seconds, and I'm going to use a 0.1 second reporting time step. Completes 1,200 function evaluations. So if I want to, I can go and animate this as well. Right, so we can still see that the system is accelerating, but for a final time of 30 seconds, which is now, I think, 15 times larger than the previous final time that we specified for the constant torque input, we can see that the acceleration of the pendulum rod is definitely or notably smaller. Now, if we go to post, the graphs will perhaps show this a bit better. And in this case, I want to go to postplot.m as well. And now I can switch on the figure 6 in this case. So I'm just going to hit Control-Shift-R, and then I can plot the third Lagrange multiplier. I know that I do have 3 Lagrange multipliers. Firstly, from the workspace, I can see that for the variable lam, it's a 301 by 3, so the number of time steps by the number of constraints that I specify on the system. And in accordance with the order in which I specified my joints as well. If I go to in joint, I first specified the revolute joint. A revolute joint has 2 constraints associated with it, an X and a Y reaction force. So those take up the first 2 constraints of this 3, and then the relative rotation driver now imposes a torque. So this is then the second joint that I specified, but it also enforces the final driver constraint that I have in this case. So this is then the third driver constraint. And this is then also where the postplot.m figure 6 comes into play. Lagrange multiplier 3 is the torque that I specify on the system. Right. I think figure 6 is actually plotting the applied torque and the inverse dynamic analysis torque in this case. What I would maybe rather do is just switch off the legend for now. And then, yeah, so I think what we can do over here as well is just switch off A1 so that we only plot A2. So A3 is simply going to be the resultant torque, so that we're going to look at in a moment when we do the inverse and the forward dynamic analysis at the same time. But for now, we just want to focus on what the effect of the inverse dynamic analysis torque is. Okay, so I'm just going to plot it like this. I think I'm happy with all of that. So if I then go over here, I did run post. So now I can just run post plot again. Okay, so starting again with figure 1, we once again see the circular profile that is traced by the pendulum rod center of mass, so that is correct. Figure 2 now shows the coordinates of the center of mass as a function of time. In this case, we can once again see that there is oscillatory effect with an increase in frequency, but the amplitude of these oscillations in the coordinates remain the same. So that also seems correct. Then figure 3 should be the, I believe this is, let me just double check. Figure 3 is then the reaction forces, so Lagrange multiplier 1 and 2. So the red line is the X reaction forces. If I go back over here. So the red line is then the X reaction forces of the revolute joint. The blue line is the Y reaction forces, and then I can simply go and calculate the resultant force using Pythagoras. And this is then given as this black line that I have over here. In this case, I see oscillatory effects in the reaction force on the revolute joint, and I also see that the amplitude is growing over here. Now, if we look at the next figure, which is in figure 4, and this is the linear accelerations. For the linear accelerations, we now see that there's still oscillatory effect, an increase in the frequency and an increase in the amplitude. So although we now specify a constant angular acceleration on the system, it doesn't necessarily mean that we're going to get constant linear accelerations for the pendulum rod as well. And this makes sense. The pendulum rod is rotating about a point, so we do expect fluctuations in the X and Y accelerations of the pendulum rod's center of mass. Okay, then figure 5 is just once again the angular position of the pendulum rod. So once again, it starts from this value, which is minus pi over 6 or minus 30 degrees, and it continues to increase since the system is in effect rotating counterclockwise. So we do expect an increase in the positional angle. Then for figure 6, we now have the torque that is applied by the driver constraint. So by the constant angular acceleration of pi over 60 radians per second squared. We can see in this case the torque also fluctuates between -6 and 6. So that's also an important evaluation over here that we can see. Previously we specified the constant torque at 6 Newton meters. In this case, we can see that if we actually want a constant angular acceleration, there has to be fluctuations in the torque. Right, and then lastly, just to make sure that that we did get a constant rotational acceleration as well, we do have this constant red line over here, which is just below 0.105, and that should this should correlate with the input rotational acceleration that we gave to the system. Okay, so that is then the case where we simply ran a inverse dynamic analysis. Now for our last step, we can go back to PR_E, and now I'm just going to activate the torque force that I have over here. So previously I just took it out of the forces list, which means it's not going to have any effect. In this case, if I now type in over here S2, then it's added back to the forces list, and now the torque is going to have an effect, and my relative rotation driver is still effective as well. So I'm essentially running a combined dynamic analysis in this case, an inverse dynamic analysis due to the relative rotation driver, and a forward dynamic analysis due to the torque specified on the pendulum rod. Okay, now in this case, I'm just going to type in DAP again, PR_E as my model folder. Yes to correct the initial conditions. And now final time, I'm going to keep it 30 seconds with a reporting time step of 0.1 seconds. If I animate the system, my expectation is that because I limit the rotational acceleration of the pendulum rod, I should see more or less the same accelerative behavior as what I saw for the case where I had just the inverse dynamics acting on the system. Okay, so we can see in this case that after 30 seconds, the acceleration of the pendulum rod is still relatively low. It's not as abrupt as we saw when we had just a constant torque on the system. Now, if I go post, and I go back to my post plot M file as well, now I have a constant torque that I apply to the system. So this is given in this case as A1. So this is one of the plots that I want to overlay on my torque plot. I just have a constant torque that I specify as 6 Newton meters. Then I'm just going to say hold on over here just to make sure that it doesn't overwrite the plot. A2 is then Lagrange multiplier 3, so the reaction torque associated with the driver constraint that I gave as input, so the constant acceleration driver. And then A3 is going to be the resultant torque that I have in this case. And that is simply whatever Lagrange multiplier 3 is, so the reaction torque plus this 6 Newton meters that I applied to the system as well. And then I'm just going to activate the legend as well, just to make it a bit easier to actually see where each of these lines lie and what label is assigned to each of them. If I'm happy with that, I can just save the script and I can head to the command window and type in post_plot. Okay, so figure 1 is once again the circular profile of the pendulum rod, so that seems correct. Figure 2 is the coordinates, the x and y coordinates of the pendulum rod center of mass. Once again, oscillatory, constant amplitude, increasing frequency. So that seems more or less the same as what I had previously. Then I have my reaction forces associated with the kinematic joint or the revolute joint that I specify for the pendulum rod. I also have the linear accelerations in this case, which also seems more or less the same as the previous case that I ran. Then in the case of figure 5, it's just the angular position, which is once again increasing. That seems correct. And now figure 6 is the figure that I want to focus on with regards to the torques. So what you'll see over here is the red line is the applied torque of 6 Newton meters. Then I have the inverse dynamic analysis torque. Now you remember previously it varied between 6 and -6 Newton meters. In this case, the inverse dynamic analysis torque actually varies between 0 and I believe this should be -12 Newton meters. And the reason for this is it has to now compensate for this 6 Newton meters constant torque that I specify on the system. So that when I calculate the resultant torque on the system, it's still oscillatory, but these resultant oscillations then cause my system to have a constant angular acceleration. And to just verify this, I can go to figure 7 and I can once again see that although I now specify a torque which aims to keep the or to oscillate the accelerations, my Lagrange multiplier or my reaction torque due to the driver constraint is in essence applying a braking torque to make sure that I always remain at this constant line that I have over here for the acceleration. So I am able to satisfy both a forward dynamic analysis and an inverse dynamic analysis. DAB-BC is able to do this internally, and we can essentially utilize the efficiency of this system to perform these type of combined dynamic analysis. Okay, so I think that was a bit of a rerun of what we did in the previous lecture. So that is then also the end of the pendulum rod examples that we wanted to look at. In the next lecture, we're going to focus on the application examples. So some of the other model folders that are available over there. Some of them are, for example, the suspension system that we can look at. We're also going to look at some combined joints. So where we have previously two distinct revolute joints, we can actually go and combine these joints to form a revolute joint or a revolute translational joint. That BC has the ability to perform these combinations if we have certain members that don't have a, a, an important mass in the system or a significant mass in the system or doesn't play a significant role. We can simply consider the joint without considering a new body in that case. But those are some of the application examples that we will be looking at starting from the next lecture. So perhaps before I end off this lecture, are there any questions regarding the work that we have done up to now? I think if you have a question, you're more than welcome to raise your hand, or you can type it in the chat messages. While you are busy typing, or if you have a question, just note that I will publish the previous lecture's video just after this lecture, and then I'll also upload the lecture material for today's lecture on Blackboard. So yeah, you should have access to the lecture video, I think, in about 10 minutes after the session has ended. All right, so I don't think we have any questions then. In that case, thank you very much, and I'll see you in the next lecture.